Hello, everyone. It's a pleasure for me to present the Professor Diego González Moreno. Diego is a full-time professor in the Department of Applied Mathematics and Systems at the UAM Coajimalpa. His research interests are in graph theory, in particular in connectivity, colorings, and cache. In this occasion, he talks on cache about and its generalization. Thanks, Diego.
Thank you, Naid. I would like to thank all the organizers of this nice conference. Especially, I would like to thank Naid, who invites me to give this talk. And I hope that you enjoy. I'm going to share my screen. So, okay. So, are you now? Can you see my screen?
Yes, on full screen, and we can hear you well.
Okay,
Yes.
Thank you very much. So I'm going to talk about caches and some of its generalizations. First, I'm going to give some basic definitions. Recall that a graph G is k-regular if every vertex of the graph has degree k. And the girth of a graph is just the length of a shortest cycle of the graph. And we said that a graph is a kg graph if it is a regular graph with girth G. For example, here we have a 3-4 graph. It's easy to see that every vertex has degree 3. And it's also easy to see that the shortest cycle of this graph is has length 4. So now we can define kg caches. So this definition is due to Todd in 47. And a kg cache is just a kg graph with the minimum possible order. And through this talk, I'm going to use n of kg to denote the order of a kg cache. So let's try to figure what are the most simple caches. We want to find what is a 2G cache, that is a 2 regular graph with girth G and the small number of vertices. It's not quite difficult to see that 2G caches are just the cycles of length G. Now, if you want to find who are the K3 caches, again, it's not hard to see that. For example, here I have a 4-3 cache. This is the complete graph on 5 vertices. So the K3 caches are complete graphs on K plus 1 vertices. And the K4 caches are bipartite graphs that have in each part K vertices. So the order of a 2G cache is G, the order of a K3 cache is K plus 1, and the order of a K4 cache is 2 times K. So these are some easy families of caches, but it's not very easy to find a cache. Let me show you how can we find a 3-5 cache. We have a 3 regular graph with girth 5. So we begin with a vertex. So since the graph is 3 regular, this vertex must have 3 neighbors. Here we have these 3 neighbors. And since the girth is 5, every vertex at the top of this graph must have 2 new neighbors and must be different. Because if they share one neighbor, a cycle of length 4 is formed, and also this vertex cannot be adjacent to this one, or we have a triangle. So the vertices of this, the 2 remaining vertices of these 3 vertices are this one, and here we have right now 10 vertices. So the vertices at the top of the graph must have degree 3, and right now has just degree 1. So now this vertex can share a neighbor with the other vertex, with some of the other vertices, and this vertex also can be adjacent to some of these vertices. So we want to add some edges between these vertices in such a way that there is no cycles of length 4 or 3, and such that every vertex has degree 3. For example, this vertex, the first vertex, can be adjacent to this one, and we have no problem. There is no cycle of length 4. And now this vertex has degree 3, so it's fixed. Now, the next vertex, now he has just forbidden vertices. For example, this vertex cannot be adjacent to this vertex because a cycle of length 4 is formed. And also, with the same reason, this vertex cannot be adjacent to this one, but this vertex can be adjacent to these two vertices. And again, it's fine because we have not made a cycle of length 4, neither a cycle of length 3. And this vertex and this vertex are fixed, so now we just need to fix these vertices. And this can be done with at these two edges. So now we have a 3-regular graph. Maybe it's not very easy to see that this graph has no cycles of length 4, but this graph is isomorphic to the Petersen graph. So the Petersen graph is the 3-5 gauge. So one natural question is that if for every k at least 2 and g at least 3, there exists a kg gauge. And this answer was responded by Erdos and Sachs in this question was responded by Erdos and Sachs in 63. They prove that for every k at least 2 and every g at least 3, there exists a kg gauge. And they also give an upper bound for the order of a kg gauge. But this upper bound is not good enough, is far away from the real value of the order of a kg gauge. But they begin to start to study the gauge problem. The gauge problem is the following. Given two integers, k and g, we need to find the order of a kg gauge. That is the minimum order of a k-regular graph with g. Here I have a table with some values of the known gauge problem, of the known values for the gauge problem. When the number is in boldface, that means that this is the exact value for the gauge. For example, with 14, the 6-regular gauge with girth 5 has 14 vertices and it's the exact value. But if they are not in boldface, they are just upper bounds. This is a very difficult problem and is still open for most of the values of k and g. So what we want to do now is to find bounds on the order of a kg gauge. And this bound is given by the famous Moore bound. So first, I'm going to show a lower bound for gauges with odd girth g. So we have one vertex. And if we are in a kg gauge, this vertex must have k neighbors. Here we have the k neighbors. And if the girth is not 3, then the neighbors of every one of these k vertices must be an independent set. So here we have these vertices. So at the moment here we have one vertex, then k vertices, which are this one, and in the next level we have k minus 1 vertices, because k vertices, this one, and each of these vertices has k minus 1 neighbors, because the other neighbor is right down. So here we have in the second level this number of vertices, and so on. In the next level, here I have k times minus 1 vertices, and from each one of these vertices, they emerge k neighbors. So I have k times k minus 1 squared vertices, and so on. And I can do this until the vertices are distance g minus 1 over 2. So this is the Moore bound for the case when the girth is odd. When the girth is even, I just need to take an edge instead of a vertex. So we begin with one edge. Here I have an edge and two vertices. And from one of these two vertices, I must have k different, k minus 1 neighbors, because this vertex has here 1 neighbor. So here we have k minus 1 vertices and k minus 1 vertices. So I have 2 times 1, this vertex, plus k minus 1, which are these vertices. And in the next level, again, if the girth is long enough, the set of vertices adjacent to this one must be an independent set. That is a set with no edges between the vertices. And here I have k minus 1, and from each of these vertices, we have k minus 1 neighbors. So I have k minus 1 squared vertices, and so on. And I can do this until the vertices are at distance g minus 2 over 2. So if we do the algebra of these sums, we have the following theorem. that says that the number of vertices in a KG cage is at least this number. And this number is very famous and is called the Moore bound. And also, we say that a KG cage is a Moore cage or a Moore graph if the order of the cage is equal to the order of the Moore bound. That is, if the cage attained the lower bound. And we know that there are not too much Moore cages. We know that there exists a Moore cage if and only if one of the following statements holds. For example, if k is equal to and the girth is at least 3, we have the cycles, there are Moore cages. And when the girth is 3 and the degree is at least 2, we have complete graphs. When the girth is 4 and k is at least 2, we have bipartite complete graphs. And when the girth is 5 and the degree is 3, we have the Peterson graph we showed before. Or when k is equal 7, we have the Hoffman-Singleton graph. And maybe, we don't know if we have a Moore cage of girth 5 and degree 57. Also, another family of Moore cages are the generalized n-gons. So I'm going to stop a little bit here and I'm going to explain which are this family with an example. I'm going to talk about the projective plane, which is a generalized n-gon. A projective plane is a set of points and a set of lines that satisfy some axioms. For example, any two distinct points determine just a line, and any two lines determine 1 point, and we have 2 points in general position, 4 points in general position. For example, here we have the Fanus plane. Here the set of points are the elements from 1 up to 7, and here I have the set of the lines. So observe that the lines are subset of points, and in this picture, we represent the line 1, 2, 4 with this line, but the line are just these points. Okay, so it's not hard to see that this set of points and lines satisfies these 3 axioms. And now, we can relate projective planes with graphs in the following way. We can associate a graph that is called the Levy graph to a projective plane in the following way. The vertices of the graph are going to be the set of points with the set of lines. And an edge is going to be, and a PL is going to be an edge of the Levy graph if and only if the point P belongs to the line L. So here I have the Fanus plane. For example, point 1 is in lines or belongs to lines 1, 2, 4, 1, 5, 7, and 1, 6, 3. So here in my Levy graph, point 1 is adjacent to line 1, 2, 4, 1, 5, 7, and 1, 3, 6. And also the line 1, 4, 2, here I have the line 1, 4, 2 in the graph, is adjacent to vertex 1, to vertex 4, and to vertex 2. So we can construct a graph from the Fanus plane, and it's not hard to see that the order of, well, that this graph is k-regular. In this case, it's 3 regular because the order of the Fanus plane is 2. So it's 2 plus 1 regular, and the girth is at least, and the girth is exactly 6. So the incidence graph of projective planes are families of cages of girth 6. And now that was a little parenthesis. I'm just going to talk about some structural properties of this family of graph. One of very important property in cages is the monotonicity property that says that if I have 3 integers k, at least 2, and g1, g2, such that g1 is less than g2, then the order of a kg1 cage is less than the order of a kg2 cage. That sounds natural. If we fix the degree and we increase the girth, it's natural that the order of a cage also increase. So this is the girth monotonicity, and a natural question is we have the same for the degree. And this is an open problem. We don't know that if K1 is less than K2, then the order of a K1 GKH is lesser than the order of a K2 GKH. So this is one open problem. I just mentioned it. But what we know, and this is true and is a very useful property, is the monotonicity. So I'm going to show you how we use the monotonicity of caches to prove some properties that they satisfy. For example, we can show that if G is a KG cache, then the diameter of G is at most G. And I'm going to show the proof because I want to see how we use the monotonicity and some ideas in order to prove some properties in caches. So suppose, by contradiction, that the diameter of a KG cache is at least G plus 1. So that means that we have two vertices, U and B, in the graph such that they are at distance the diameter that is at least times G minus 1. So here we have this picture. Here we have my two vertices, U and B, which are at distance at least G minus 1. So the distance between the neighbors of U and the neighbors of B must be at least G minus 1, because they are at least, U and B are at distance at least G plus 1. So what we are going to do now is we're going to construct a new graph, G star, in the following way. We delete the vertices U and B from G and add a new set of edges, E star, which is a matching between the neighbors of U and B. Since we have here K vertices and here another K vertices, we can have a match between the neighbors of U and the neighbors of B. So the red edges are precisely the edges in E star. So we have now constructed this new graph and observe that this graph is K-regular because every vertex here in G star, in G was adjacent to U. Now we delete this edge, but we have another edge with to every vertex. So this graph is K-regular. And what we want to do now is to show that this graph also has girth at least G in order to use the girth monotonicity. So suppose that C is a cycle of this new graph G star. If the edges of this cycle C intersection with the set of edges, red edges, E star, is empty, then that means that this cycle was an original cycle of the graph G. So since G was a KG cache, these cycles must have length at least G. If the cycle C has one red edge, sorry, my mistake, it should be a star, not instead of a 2. So if the edges of the cycles have one red edge, then here we have this situation. Here we have a cycle with one red edge. And since the distance between these two vertices are at distance G minus 1, that's by construction, then the length of this cycle is at least this distance between these two vertices, which is at least G minus 1, plus this edge, which is G minus 1 plus 1, which is G. So the length of these cycles is at least G. And, okay. And the cycle C has at least two red edges. Here we have the following situation, and observe that these two vertices can satisfy two things. The first one is that both are neighbors of U or both are neighbors of B. In that case, they are at distance G minus 2. Or one is neighbor of U and the other one is neighbor of B. So they are at distance G minus 1. So the distance between these two vertices is at least G minus 2. And the same occurs with the other two vertices. So the length of this cycle is at least 2 times G minus 2 plus 2, which is at least G. So what we have shown is that G star is a KG star graph. The girth is G star. We don't know which is the girth, but we just know that this girth G star is at least G. And by the monotonicity theorem, we know that the order of the graph G star, which is a KG star graph, is at least the order of a KG star cage. And this number is equal to the order of G minus 2 because we delete two vertices, U and B. And this is the order of a KG cage minus 2, which is less than the order of a KG cage. And this is a contradiction due to the monotonicity theorem. So that's a way that we can use the monotonicity theorem to prove some properties of cages. Another important property that can be studied using cages is another interesting property in cages is the monotony, the connectivity. Recall that a graph G is K-connected if it has connectivity at least K. That is, that I need to delete at least K vertices to disconnect the graph. In 1998, Fu, Wang, and Roger proved that every KG cage is two-connected, and they use the monotonicity theorem. I'm going to show again just the idea of the sketch of the proof. We assume that we have a KG cage that has a vertex cut, that is a vertex U, such that when we delete U from G, the graph is not connected. And consider a minimum component of G minus U. So here we have the picture, here we have my minimum connected component, and here in this case, we do the same thing. We construct a new graph with less vertices than the original graph, and in such a way that the resulting graph is regular and has girth at least G. So in this case, we consider a copy of H, and we have a matching between every vertex with its copy in H prime. This graph is K-regular because this vertex lose one edge, but we have one edge. So this graph is K-regular, and with similar ideas, we can prove that this graph is also has girth at least G. So again, with the monotonicity theorem, we can show that we obtain a contradiction, and we can show that the graph cannot have a vertex cut. Okay, so concerning this conjecture that has been widely studied, we know that this conjecture is true when the girth is 3 or 4, or when the K is 2, 3, or 4, or when the girth is 6, 8, or 12, or when the girth is 5, 7, or 11, and K minus 1 is a prime power. In general, the best known result for the connectivity of KG cages are these two results. Well, is K connected? Is T connected? Where T is the largest number that satisfies this inequality. And we know also that cages without girth, at least 7, are K over 2 connected, more or less. And concerning the edge connectivity, is known that KG cages are maximally connected. It's more easy to study connectivity, edge connectivity in cages than vertex connectivity. Okay, so now I'm going to present some open problems in cages. There are all conjectures. We don't know if every KG cage with even girth is bipartite. They conjecture that every KG cage with even girth is bipartite, but at the moment, we don't know too much about this conjecture. Also, we have the degree monotonicity, that if n of kg is less than n of k plus 1g, if we fix the girth and increase the degree, it's true that the order of the kg cage increase. Also, another conjecture is that every kg cage with girth odd has a cycle of length g plus 1. Another conjecture is that every kg cage is superconnected and are superconnected. Superconnected means that if we want to disconnect a kg cage by deleting k vertices, the only way to do that is by removing the neighbor of a vertex, or by removing the edge neighbor of a vertex. That means superconnected and are superconnected. And also, a very famous open problem in cages is determine if there exists a 57.5 Moore cage or not. At the moment, we don't know that. So I want to talk about cages and some generalization of cages. So one natural generalization or one natural question of cages is what happened in the directed case? So what happened with directed cages? Some definitions for directed graphs is that a digraph D is said to be D-regular if the out degree and the in degree of every vertex is equal to D. The girth of a D-graph is the same as in graphs, is the length of a shortest directed cycle of the digraph. And we said that a directed TG cage is a D-regular graph with girth G and the small possible order. And we are going to use G of DG to denote the order of a KG cage. And for example, here we have a 2-5 directed cage. Every vertex is 2 regular, has 2 arcs outgoing and 2 arcs incoming, and you can see that the length of a shorted cycle is 5. So Besat, Charter, and Wall in 69 gave a construction for directed graphs with girth G. If D is at least 1 and G is at least 3, we can construct a circulant digraph that is a digraph where the vertices are the integers modulo this number, and the out neighbor of every vertex are this set of vertices. That means if I have one vertex, we just make it adjacent to the following, to the next D vertices. So since we are, in this case, we have the 3-6 cage. So this vertex is adjacent to the next 3 vertices, and the next vertex is adjacent to the following 3 vertices, and so on. So this graph is going to be a D-regular graph, and is going to have girth G. So this is a construction of DG graphs that give us an upper bound for the order of a DG cage. And in fact, in the same year, they conjecture that the order of a DG cage is exactly that number. And this conjecture in the same paper was established in a similar way. That is an equivalent conjecture that says that if T is a D-regular digraph of order n, then the girth of the digraph is at most the floor of n over D. And if we relax the regularity condition, we have a very famous conjecture in graph theory, the Cachet and Hackwick's conjecture, that established that if this is a digraph of order n and every vertex has out degree at least D, then the girth of the digraph is at most the floor of n over D. And this is a very famous conjecture which is closely related with the case of directed cages. Here we have a short resume of results concerning the Cachet-Hackwick conjecture. We know that this conjecture is true when the degree is 2, or when the degree is t, or when the degree is 4 or 5, or when the degree is at most the square root of n over 2. Okay, but let me see something. When we talk about the girth in the graph, we mean in some way that we want that the graph have holes of some length. But here in the directed case, if you see this digraph, well, here we have a transitive tournament of order 3. Yes, this is not a directed cycle, but in some sense, this digraph has triangles, not directed triangles, but the digraph has triangles, so it has no very big holes. So in order to explore the spirit of the girth in graph 2 digraphs, we are going to present the k-geodetic cages. So let me give a definition. We said that a digraph D is k-geodetic if for every pair of vertices of the digraph, U and B, there is at most one walk of length at most k. For example, here we have a two-geodectic graph. If you observe this vertex and these two vertex, there are just one side, one walk of length at most one, or at most two, sorry. We have this one walk, and there is no other walk of length at most two between these two vertices. So these are two geodectic graphs. And we can define the geodetic girth of a digraph, which is the largest value of k such that D is k geodetic. And observe that if D is k geodetic, then the girth of the digraph is at least k plus 1. Because, for example, here we have a directed triangle. We can assume that that between every vertex we have, if we want to go from U to the same vertex U, we can have, in this example, this 3 cycle, which is a walk of length 3, and we can consider that the vertex U is a trivial walk of length 0. So here we have this closed walk and the trivial walk, so it cannot be a 3 geodetic graph. Okay. So as in the case problem, we can define the geodesity problem. That is to find the smallest possible order of a digraph with minimum of degree D and geodetic girth K. And Ersin and Tweet recently, 2019, defined the dk geodetic caches as a k-geodetic digraph with minimum of degree D and geodetic. The geodetic graph with minimum of degree D, and they use n of the key to denote the order of the key geodetic cache. And similar to the Moore bound for caches, here we have this lower bound for the order of the key geodetic cache. And again, a natural question is, for every pair of integers k and g, there exists a geodetic cache. And yes, Ersin and Tweet, James Tweet, proved that for every d and k, at least 2, there exists a k geodetic cache. In fact, they gave a family of graphs that produce k geodetic caches. And this family are the permutation digraph. If d and k are integers at least 2, the permutation digraph that we denote as p of dk is denoted as the following graph. We have the vertices of this digraph are the permutation of length k of symbols in this set. And a vertex of this form is going to be adjacent to all the permutation of this form. That is, you just observe, we just remove this first vertex and we have another element at the final. For example, here we have the vertex 01, which is adjacent to 1, 3, and 1, 2, 2. So this is a well-known family in the digraph world. And this family of graphs are k-geodetic, not k-geodetic caches, but dk geodetic graphs. So this family of graphs gives the existence of k-geodetic caches. And again, when we are studying the family of caches, every cache, every generalization of cache, we want to study some structural properties. And for that purpose, it's useful to have the monotonicity theorem. And they prove in the same paper that the monotonicity theorem holds for k-geodetic caches. And with this property, they can prove that all directed caches are strongly connected. And in fact, we have also conjectures concerning k-geodetic caches that are maximally connected and super connected, similar to caches. Okay, so I'm going to finish this talk with some other generalization of caches. The first one is DG cache. If we relax the degree, the regularity degree condition of a KG cage, we can have the DG cages that are cages having whose vertices, that are graphs whose vertex set is in the whose degree set is D, has GERD G, and has the least possible order. Or we also have the GERD cages. These cages are regular graphs, K-regular graphs with odd GERD G, even GERD H, that is the length of a minimum odd cycle is G, and the length of a minimum even cycle is H, and has the least possible order. Another family of cages are Cayley cages that are KG graphs, that is K-regular graphs with GERD G, but they also need to be Cayley cages and also have the smallest possible order. And recently, we have, well, there is a new family of cages that have been studied that are the mixed cages. Mixed cages, well, first, a mixed graph is a graph that have edges and arcs. And a mixed graph G is going to be zeta arc regular if the H degree is arc and the arc degree is D. That is, for every vertex, the arcs outgoing from every vertex and the arcs incoming from every vertex are zeta. And the GERD is defined as the same in the other families. And zeta RG cage is a mixed cage if it's a zeta regular graph with GERD G and the least possible order. And they can also define the mixed geodetic cages that are mixed graphs that are also K-geodetic cages. And there are a lot of generalizations. In fact, you can think in a property like being Hamiltonian and consider regular graphs with GERD G and that are also Hamiltonian and the smallest number of vertices. So I believe that I'm going to leave this talk here, and thank you very much for your attention.
Thanks, Diego. Have a nice talk. Do you have any question?
Yes, I have. Can I?
Yes.
First of all, thank you very much for the talk. Last time, I was forced to get to be familiar with cages in considering another problem, but we are interested in graphs of GERF exactly equal to 5. And as you mentioned, we have only some K-regular graphs with GERF 5 with the smallest number of vertices. Yes, it's for K equal to 3. It's a Petersen graph, Hoffman-Singleton graph, and I would like to ask you about the situation with 57 regular graphs. What is the state of the art? Why we don't know whether there is such a graph or not?
Yes, that's a nice question, and that's a nice question. When they prove that there are more cages of GERD 5 only when the regularity is 3, 5, 7, or maybe 57, that was a spectral proof. So in the proof, they find at the end, I don't remember really well now, but at the end, they have some possibilities that if that cage exists, the K must be 5, 7, or 57. And they found the Petersen graph, the Hoffman-Singleton, but at the moment they are not be, well, at the moment they can't find we're not able to find these 57 regular graphs. As far as I know, Professor Exo is right now having a computer program trying to construct this 57 5 GERD, and as far as I know, this program will have maybe 1 or 2 years running, and at the moment there is no result. But we don't know if that cage exists, but we know a lot of things about that possible cage. We know maybe if that exists, it should have some automorphism room, and we know a lot of properties that in case of that cage exists, that will happen. But at the moment, we are not able to find it. And
Okay.
yeah,
But in the case of 7 regular graph, is the only Hoffman singleton graph, yes? Is the only one such a graph?
yes, I believe that is the only one.
Okay. Okay, so once again, thank you very much for your talk.
Uh,
Very nice.
Thank you.
I have 2 comments. Julian said, nice talk, Diego, and Rita said the same.
Thank you.
Any another question? I wait
There are
because
no questions in YouTube. No.
Okay. I wait or not, Rita?
Okay, I think we can continue, and if we receive some questions in Face, we will send to Diego as the rest of the speakers. Thank you.
Thank you very much, Rita.
So thank you, Diego.
Thank you, Diego.
Thank you again for the invitation, and thank you everybody to be here.
Thanks.
So Nait, maybe, okay, maybe we like to remember the people that now you can see the videos of today and the poster when we finish by Facebook, and tomorrow is the last day, and we will have our invited speakers, Diana and Ella. So we wait for everybody tomorrow, the same time, the same channel, but different speakers. So I don't know if somebody have another announcement, or we can finish for today. No?
Nope.
No? Okay. So thank you very much. See you tomorrow.
Thank you.
Bye-bye.
Bye.
Bye.
Juli, no nos cortes que... Uy.